Alright, so here we're looking at this idea of pressure. Now, pressure was brought in because of the idea that a force, when it's concentrated over a certain area, would have a different effect. Obviously, if you're concentrating a force in a small area, that effect would be greater than if you concentrate a force over a large area. So the formula that we have for this is that the pressure is equal to the force divided by area. Obviously, it's going to be a Newton meters to the minus 2, your Newton per meter squared. And we've got a new unit for this. We call this Newton meter to the minus 2, we call that a Pascal, or a PA for short for that. So that is a Newton per square meter. Okay, now looking at this idea of an ideal gas and a real gas. An ideal gas was developed as an idea to work with gases at sort of regular temperatures, and they obey this law or this equation: PV is equal to nRT, where, let me write it over here, PV is equal to nRT. You don't actually need to work with this in the standard level curriculum, but obviously P is your pressure, V is your volume, N is the number of moles, T is your temperature in Kelvin, and R is the universal gas constant. Alright, so that is the formula. So a ideal gas will obey this law under all equations. Basically, it means that the gas cannot be liquefied. Now, in a real gas, we'll come and looking at a real gas now, but these are the postulates of an ideal gas. And the idea is that they consist of tiny particles called atoms, molecules. They actually look at them as spheres. We have got a large number of particles. They are in constant random motion. The range of intermolecular forces is small compared to the average separation. In fact, we assume that there are no intermolecular forces. There are no intermolecular forces. The only forces when they actually bump into each other. So here it is: no forces act between the particles except when they collide. And between collisions, the particles move in straight lines. These collisions, we say these are elastic collisions. In other words, they don't lose any kinetic energy, and they obey the Newton's laws of motion. Now let me just bring up this simulation that we've used before. This would be an idea of an ideal gas. As you can see, particles are moving all over here. They're moving to and fro, they're bumping into each other, but they are not losing, the temperature is not going down, the kinetic energy is remaining the same, the average kinetic energy is remaining the same. Now as a particle hits, so as a particle comes in and hits there and maybe bounces off, we can see that there is going to be a change in momentum, because the velocity would be in this direction, the velocity would be in this direction. So there is a change in velocity, so change in momentum, and that means that there must be a force being applied, because we know F times the change in time is equal to the change in momentum, the impulse, and so there's a force applied. So the more particles that are hitting and the quicker they're hitting per unit area, the greater is going to be the pressure. So that's where the pressure comes from. It's these particles hitting, changing their momentum, applying a force, and therefore applying a pressure. Okay, now as I change the conditions here, perhaps I cool this down. I let the temperature drop, and I'm going to increase the pressure. I'll push this in somewhat. Let me put some more gas in here. Now, an ideal gas, or gas behaves like an ideal gas when there are low pressures and high temperatures. Low pressures, high temperatures, that's the sort of conditions that you're going to get behaving like an ideal gas. When you get it that the temperature is low but your pressure becomes comparatively quite big, then the particles themselves become quite close together, and then you can get these intermolecular forces starting to hold. So you may get some holding on between these particles because they're so close together. They're not moving very quickly, so these intermolecular forces become strong enough to start to have an effect. Then a gas will no longer behave like an ideal gas. It'll behave like a real gas. So when the pressures are quite high, when the pressures are quite low and the temperature is quite high, we have gases behave generally like an ideal gas.